Let's find the critical values of x. Now this function here involves a fractional exponent multiplied by 2 minus x. This looks like a nice product rule question. This is our f, this is our g. And recall that when you have y and you want to find y prime of this product being multiplied, it's going to be fig plus gif. So fig happens to be f prime multiplied by g. So the derivative of x to the 2/3 using power rule is going to be 2/3 x to the 2/3 minus 1, which is the same thing as minus 3/3. And g happens to be bracket 2 minus x plus g prime, which happens to be derivative of this is the coefficient -1, multiplied by f, which is x to the 2/3. So I'm just going to simplify this fractional exponent here. 2 minus 3 is negative 1/3. So what we have here is x to the -1/3. I'm going to move that to the denominator. X to the -1/3 becomes x to the 1/3 on the bottom. So we have x to the 1/3, or that also means cube root of x. We'll just leave it as fractional exponents for now. And the 2 minus x remains on the numerator, which is the answer. Plus bracket minus becomes a minus, and we have x to the 2/3. Now normally we're thinking about the derivative, the slope, critical points being the slope is 0. But another big rule you need to remember is that the critical point is also where the slope is undefined. So even for a split second, the denominator being 0 causes a problem with the slope formula. You can't divide by 0 in math. It's a big rule in math. You can't divide by 0, you can't take the square root of a negative number. So here, when x is 0, when x equals 0, the y prime is undefined. So therefore, x equals 0 is a critical point. This is a country boundary. So this crazy graph here, when you have x equals 0, there's actually a boundary line. Right here, something strange might happen, whether the function is increasing, decreasing, who knows what. But this is definitely a candidate for a country border wall. Now let's focus on the other critical values of x. Yes, 0 is a critical point. The other critical values is when the derivative, the slope, is 0. So now let's just practice our algebra. So I just copied where we're at here. 0 is a slope equals this expression here. We're going to throw this negative term over, and now we have x to the 2/3 is equals to 2 bracket 2 minus x, 3x to the 1/3. Now how do we solve this expression? Let's use some clever algebra and multiply top and bottom by the same number. You're allowed to do that in math. And what clever number can we think of? Let's think of x to the 2/3. So as a fair Texas judge, we're going to multiply top and bottom by x to the 2/3, which cancels out to be 1. That's okay. And why would we do that? Is because when we add these exponents, 1/3 plus 2/3 is 1. It ends up being nice and clean. So what happens now is that the numerator here is x to the 2/3, and the numerator here is x to the 2/3. When there's an equal sign, you're allowed to divide both sides by x to the 2/3. So essentially, this cancels out, and it cancels out, and this becomes a 1. Because x to the 2/3 divided by x to the 2/3 becomes 1. X to the 2/3, when you divide it, it cancels out, and this becomes a 1. 1 times anything is itself. So let's clean this up here a little bit. 1 is equals to 2 minus x, 3, and now we're adding the exponents here. 1/3 plus 2/3 is 1, so we just have an x here. And this question doesn't seem that hard anymore. You could say 1/1, same thing. You can cross multiply. So now we have 1 times 3x is 3x, and 1 times anything is itself. So what is this expression here? You can simply do polynomial expansion. 3x is equals to 4 minus 2x, and now this looks like an elementary algebra problem. The negative 2x goes over. We have 3x plus 2x is going to be 5x equals 4 So therefore x equals 4 over 5, which is equals to 0.8. So the question was asking for, what are the critical values of x? Yes, we found 0, because we're going to respect undefined slope as a critical point, as well as x equals 0.8 or 4/5. Now let's just take a peek at Desmos, our good friend, to see what this function actually looks like. So we punched it in here. We have f of x equals x 2/3 multiplied by 2 minus x. And indeed, we have to be careful. The slope here at this nice corner, or we call this cusp, where it's very kind of curved and sharp like a tooth, is the slope is undefined. And yet the derivative is decreasing on the left and it's increasing on the right. And again, the slope here is 0 at 0.8, x equals 0.8, just like how we computed. And we have to be careful. This is a good candidate for the slopes being changing from increasing to decreasing. And when we have the shape here going up and then down from left to right, this is called a maximum or local maximum. So let's just finish this off here. We answered the question, the x-coordinate of local max. In order to do that, the critical values, by the way, is going to be 0, comma, it's going to be 4/5, as we computed previously. Now these are country boundaries. We have x equals 0 here, and this is going to be 1, but here the boundary is going to be 4/5, or x equals 0.8. Now let's do the boundary test. Let's pick a number to the left of 0, the critical value. Let's pick a country, Canada, being on this side here, and let's pick the Canadian -1 as a value. Let's pick a value here. Let's just pick 0.5. Canada, USA, Mexico. And then what about Mexico here on the right? Why don't we pick a nice whole number here, 1. So all we have to do is plug these test points into the actual derivative formula. Now unfortunately this derivative formula is not so nice, so ideally we'd have a calculator. So the derivative formula, y equals this here, can be used when we're plugging in test points. -1 is the Canadian country here. We're going to substitute -1 into all occurrences of x here. Let's at least do one question here. So y prime, the slope, is going to be 2 minus that x value, which is -1, 3, -1 to the 1/3, all minus -1 to the 2/3. So punch this into your calculator, and the answer should be -3. Let's verify this result. -3, a negative slope means the function is decreasing left to right. And you would repeat it for USA and Mexico. These little boundaries here are critical points where the derivative is either 0 or undefined. So let's go to Desmos. So as you can see, here's the original function in Desmos. And here's where x equals 0, the derivative is undefined. And another critical point here is going to be x equals the 0.8, which is going to be the local maximum. But we tested out the value -1. At x equals -1, which is here, we were finding the actual slope. And the slope here is going to be downhill. Why don't we actually use this feature of Desmos, which is a built-in f prime of x. So I'm going to click here. The red graph is the derivative graph. So at x equals -1, the derivative of the black graph, the original function, is going to be -3. So indeed, this graph here is downhill. The graph is decreasing. So to find the x-coordinate of the local maximum, focus on the black graph. You would continue your boundary tests, and you would figure out that the second part, USA, is going to be increasing, and then the third part is going to be decreasing. So definitely the x value of 0.8 would need to be plugged back into your original f of x function to get the y value of 1.034. So this would be the coordinates of the local maximum.